So, what did we do? What did we do in those activities this week? So we took a track and we had a ball on that track and we put the ball at different heights, right? We also took that track and we were able to change the angles, but we always started at about the same height, right? So when we did this, we're not changing the height, we're not changing the mass of the ball. What are we changing? The angle, which is also changing what else? No, it's changing this. See that? You're changing the length of that incline. Okay? So you're managing to change the length of the incline when you're changing the angle. So when we went back at the very beginning of the chapter, we had that, what do you think? And we had those two tracks, one with a steeper incline, one with a shallower incline, but both carts were starting at the exact same height. And most of you guys, if not all of you, said that the one with the steeper incline was going to be funner. And the reason why it was going to be funner is because it was going to go faster. Right? Is that true? Did this ball here, starting at the same height but at a different angle, did it go faster? No? Yes? I don't remember. That was an experiment. We're not supposed to learn anything from experiments?
I never talked about this.
We did talk about it. So, what did you guys find? Yeah, seriously. What did you guys find? Anyone? What did you find? When you changed the angle but kept the height the same, what did you find? What happened to the speed? Did it change? It didn't change. The speed stayed the same. If it started at the same height, we had the same speed. So when we had that height, we had the same speed. So if we kept it at 15 centimeters high, we could always figure out what the speed is at the bottom. Okay? We could always figure that out. So the important thing when looking at the speed of an object as it's going down an incline is how high it starts. Not necessarily the geometry of the incline. When you curved it, but you started at the exact same height, did it change anything? No, it all moved at the exact same speed, or at least approximately. There is a couple of things that do change, and that's friction, but we're not going to talk about that. Okay, cool? Everybody understand that? So the height is what determines the speed, not the incline. The incline does make it funner, though. The reason why this one is going to be funner than this one, depending on your tolerance for terror, that one is steeper. So it gets up to the speed faster than this one. It takes less time for that ball to get up to its speed than this one. Imagine if that incline was even like this. It's going to take a long time. It's going to take a long time for that object to get up to the same speed as it's going to take for this object. This one's going to experience a much slower acceleration than that object. Okay? Cool? But they both get to the same speed. Everyone get that? Alright, so in this chapter we had a couple of vocabulary words. Gravitational potential energy. Somebody want to explain to me what gravitational potential energy is? And it's written as GPE. GPE.
It's like the energy that something has, I guess like because of its position in gravitational fields.
Okay. So in physics, the word potential energy, the P in GPE, means that it's positional-based energy. If it has the word potential, it means that it's positional-based energy. Go around.
Oh, I didn't notice that.
Okay? It means it's positional-based energy. But gravitational energy is height. That's what we mean when we talk about positional-based energy. The higher it is, the more gravitational potential energy it has. Okay? That's the position we're talking about. We're talking about its height. Okay? Cool? How about the equation for gravitational potential energy?
The equation?
Yeah.
Mass of object times strength of gravitational field times height.
Yeah.
MGH. Okay, so this is the mass of the object. What's the units of mass?
Grams.
Grams or kilograms? Okay. G is?
Strength of gravitational field.
Yeah, it's got another term.
What?
It's called the acceleration due to gravity.
Oh, acceleration.
Okay. That's a better term than the strength of the gravitational field, because it's not really a gravitational field equation. Okay. It's the acceleration due to gravity, and that is always what number when we're talking about Earth? It's one particular number when you're talking about the Earth. Well, let me tell you. (10 meters per second per second). Or 9.8, that's the actual value. 10's a lot easier to do the math. Okay? Multiplied by the height gives me the amount of energy that that object has. Okay? The other thing that's kind of interesting is this right here, this mg. You guys remember seeing that before?
Oh.
It's the weight. Remember when we were talking about the difference between weight and mass? Mg is the weight of an object. How much it's being pulled down by. So how much it's being pulled down by multiplied how high it is the amount of energy it has. Cool? So that's gravitational potential energy, mgh. We give the equation mass times the acceleration due to gravity times the height. The mass in kilograms, the acceleration due to gravity is 10 meters per second at the Earth. And then the height, and that should be in meters, but I'm not going to be that big of a stickler about that. Cool? Make sense? And that is a joule, named after a doctor, Prescott Joule, who decided that human blood carried energy. The other type of energy we talked about was kinetic energy. What is kinetic energy? Go ahead.
Well, it's kind of the energy of an object possesses because of its speed.
Okay.
It progresses.
So it's the energy of an object based on its motion, how fast it's moving. More motion, more kinetic energy. Okay? So it's energy based on its motion. Cool? What's the equation for kinetic energy?
1/2 times mass of object times speed. Or mass of object times speed squared divided by 2.
1/2 mv squared.
Yep. Or mv squared divided by 2.
Cool. So mass again is showing up there. Looks like an object has to have mass in order to have energy. That's not quite true, but for the most part it is. And then v is velocity. It's another term for speed. Okay.
Velocity is kind of a little different from speed.
It's a little bit different, but it's very similar to it.
So you cancel the two speed and velocity sometimes.
Sometimes, especially in energy, you can substitute speed for velocity.
So, in any time that we're dealing with energy, you can always substitute speed for velocity?
Yep, absolutely. Absolutely. So, half the mass times the speed squared. Okay? That's kinetic energy. That's the energy of motion. There's no position in here. There's no height. There's no length. There's no distance. Like in potential energy. That's why it's called kinetic energy. It's motion. It's all about its movement. The way I like to think about kinetic energy is I like to think about kinetic energy as a hippie and potential energy as a yuppie.
As a yuppie?
Yeah.
What's a yuppie?
You don't know what a yuppie is?
No, I'm sorry, I don't understand what you know.
What's a yuppie, guys? My brother's a yuppie. What's a yuppie? What? A what? A baby? I didn't hear you. A yuppie is somebody that is only interested in improving their station in life. They're all the phrase "keeping up with the Joneses" kind of describes what a yuppie is. He's concerned about his position in life, and he wants to be in a higher position than everybody else. So that's why.
That's gonna be a little hard.
That's why it's a yuppie, because it cares where it's at. It wants to be above everybody else. It cares where it's at. What's a hippie?
Yo, dude, let's have world peace.
Let's go out and do some surfing, man. Let's go hang out in some commune, man. Not always.
Tree huggers.
Tree huggers, that sort of thing. It's about the trip with a... Guys, it's about the trip with a hippie. They're like going somewhere. Okay? So they're all about the journey. They're all about the traveling. They're all about the trip. These guys are all about where they are related to everybody else. Yuppie, hippie. Okay? Cool? What other interesting thing did we find out in this experiment?
The experiment?
Anybody find out anything really interesting? One of the most important laws of physics is in this experiment.
What color? Wait, no. Laws of physics?
Yes. It's called the conservation of energy.
Alright.
Okay? Conservation of energy is one of the most important laws in physics. As a matter of fact, the conservation of energy laws can supersede Newton's 3 laws of motion. The energy law is far more important than F equals ma. Okay? So it's conservation of energy. So what does it mean to be conserved? Yeah, what does it mean to conserve? To store, to save, to retain everything you have, right? So the conservation of energy says that I'm going to keep my energy. I may transform it. I may take some of my potential energy and turn it into kinetic energy, or take some of my kinetic energy and turn it into potential energy. But the numerical value, the amount of energy that I do have, is conserved. So if I have 100 joules of energy, I always have 100 joules of energy. I may have 50 joules here and 50 joules here, 25 joules here, 75, but it always is going to equal 100 joules of energy. Okay? So that's the big thing about this whole experiment, is the conservation of energy. That the amount of energy I start off with is always the amount of energy I end up with. Okay? That's not always true, but we'll believe it for now. Cool?
Yes.
Everybody all right with that?
I guess.
So, how many of you have started the FED assignment and have almost got it done?
That assignment?
Oh, there's my... That's...
Simulator, did you not see every single time the skater went all the spins and break? That's good enough.
Alright, that was fun.
What's that? You started, not everyone's finished?
Well, I'm number 3.
You're on number 3?